Okay, so this is an AC generator problem. It says it in the title, but say that that title wasn't there. You know, say that it didn't say anything and it just said problem number whatever on the test. How would you know it's a generator problem? You got to read it, and that's a part of this last module is being able to turn variables or terms into usable things, grabbing the useful information. And that's because in the real world, you know, you may not know what it is off of my generator that I have to go read. And so this is a lot of terms here, but this first part, three-phase, it's just telling me that that's a three-phase generator, which now I know at least the power has three phases. It's Y-connected. Most generators are, especially in this class. Two poles, right? That's the term poles. It depends on the magnet that's spinning inside of the coils of wire, affects our system. 60 hertz is what most everything in America is, so it's F if we're talking about power. And right here is the main word. I see the word generator. If I see the word generator and I'm a student in this class, I now know whatever I was thinking beforehand about the problem, at least these formulas are going to be involved. Okay? That's because it's everything inside of three-phase generator. So if it's the only spot where the generator is discussed, it's probably the formulas that I need to know. And here's the term poles, right? That's telling us something about its speed based off its how this generator is made up. And this generator is generating electricity going from using mechanical energy to make electrical energy. So now let's see which of these terms are what we're going to need to solve. There's a lot of information in here. If you wanted to solve them, write them all out, you could. Right here, VA is S, right? Apparent power. And I'll say it's S rated. And the reason why I'm distinguishing that is because down here, it gives us an actual condition. So think about your car engine, you know, is rated to go, even on your speedometer, it probably says 120 miles, 150 miles an hour. But your actual condition, if you're on the highway, is about 70, maybe 80 if you're, you know, have a lead foot. So but that's the actual conditions. It's rated to go higher. So we have to read in the problem which one is that we're going to use. Because here's S rated in the actual load. Here's kilowatts, right? And that would be P actual. But either way, it's what's coming out of the generator. If I think back to the beginning of the class or just everything that we've been doing, and then I have a system right here and like here's my load, what this whole power flow diagram is saying is that inside of this little circle that we've been drawing, there's like a power coming out of it. Does that make sense? And so if this is electrical power coming out, that's what's happening inside of this little generator that we've been drawing. The whole time we've just been modeling it like this, and now we're seeing how is this sinusoidal wave actually being created. And so if it's the actual, so it says determine the reactive and apparent power delivered by the generator. So that means if it's the power delivered, this would be the actual. And I think this one is even a little poorly worded. I think it could say actually delivered by the generator, but it would use the word rated to deliver if we were looking at what was being the rated to deliver. Okay, so there's enough conceptual stuff. Now let's just talk about solving it. So it says determine the reactive and apparent power delivered by the generator. So I have a power factor of 0.6, FP equals 0.6. So if I'm looking at the power triangle, I have P, and if I take cosine inverse of 0.6, that would give me the theta angle. There's other ways to do it. For me, it's pretty easy to at least find these terms inside of here. And so that angle cosine 0.6, and I get 53.1 0.13 degrees. That's the theta S inside of here. Another way to solve, if you have two, and I'm doing that to remind you that if you have two parts, if you have a power factor in one, you can always find the other two parts of the power triangle. P over S is also equal to the power factor. So if I needed S, well, it's P divided by FP. So 900 divided by 0.6 gives me 1500 VA. Okay, so there's the first part, the reactive and apparent power. There's the apparent power S. Reactive, there's multiple ways to get it. You could use using the tangent, right, back to Chief Sokotoa. The tangent is opposite over adjacent. You could do that. You could also use Pythagorean's theorem, say 1500 squared minus 900 squared, and take its square root, and that would also give me Q. So Q in this case is 1200 kVAR, and it's inductive. And the reason I knew that is because it was a lagging power factor. And in the real world, almost all loads are inductive, so that's most common. So there's 1200. Here's my two parts.
So how did you know to use a 0.6 instead of the 0.8 power factor?
Because in the problem statement, it says determine the reactive and apparent power delivered by the generator. So I need the actual. So if it said rated to deliver, then I would grab the 0.8. But because it said delivered by the generator, and I think it should even be more clear, and on the exam, if it gave you both, it would be more clear and say actually delivered by the generator or delivered under actual loads or under actual conditions. It would probably be a little bit more clear on the test. But in the real world, I mean, that's something that you would need to be able to do yourself as far as, wait, which one am I looking at here? You know, if I have a load and I have a generator rating, am I solving with the generator rating or am I solving with the actual load? So the first part says determine the reactive and apparent power delivered by the generator. We've done that. That was part A. Part B says find the current delivered by the generator and include the angle of I. So from here, there's two ways that you could do it. I will show the way that's on the formula sheet, the most straightforward. And if you want to see the other way, remember yesterday in class, I gave that other example. You can look at that. The other way would be to take, I'll just write the formula down, the I complex conjugate. And then just remember, I said that you had to take the S of a single phase and the V of a single phase, and that will give me the I of a single phase. It's a Y connected, so that I is the I line that we're being asked to solve for. Find the current delivered by the generator. That is that I. So the V of a single phase, I would have to simplify, I'd have to divide the 450, right, by √3, because that's a line voltage. I need a phase voltage. And the S of a single phase, well, this is S total. So I would need to divide that 1500 by 3, and I could solve for I. But the way on the formula sheet, if the equation sheet, right here, it says P out equals √3 V line I line cosine theta. So if I'm writing that down, P out equals √3 V line I line cosine theta. This is part B. Okay, P out, I was already given 900 kilowatts, √3. V line was given in my problem statement, 450 volts. It doesn't say it on the equation sheet with these absolute values, but it is just the magnitude. Notice how on the equation sheet it's not bolded and it's doesn't have a vector on top, so it's just the magnitudes. And in cosine theta here, well, what else do we know of cosine theta? Cosine theta is the power factor, right? Power factor, look over here, I already wrote that, power factor cosine theta. So now I can calculate the magnitude of I line, cosine theta, 0.6. We're still looking under actual conditions. And so I can calculate the magnitude of I line by just dividing those. And the I line is 1.92 kiloamps. How do I get the angle? Let's make sure that it even says it. It doesn't, and it probably should. So you can assume, I'll just write it down here. Assume reference phasor, EAN. So if EAN is my reference phasor, that's like saying theta V equals 0. So if theta V is 0, then theta S of the power triangle, theta V minus theta I, well, this one is 0. So theta I that I'm being asked to solve for is just negative theta S. We already had theta S up above as 53.13 right here. So now I can combine both of those together. And I can say that I line, or I delivered, IA, is 1.92 kiloamps, angle negative 53.13. Okay. That stuff up above in red is from the last problem. Okay, the last one says, what is the overall efficiency? What is efficiency? C, efficiency is P out over P in. I know P out, 900 kilowatts. I don't know P in. On the equation sheet, right inside of here, I can get P in by adding up my mechanical loss, my electric loss, and my P out. Mechanical loss, notice how there's no formula here. It'll just be a given. Okay, so look in the problem statement for your mechanical loss. The electric loss, I'll solve for. Well, I just solved for I line, so we need to use our armature. Armature just means coils. Let's see what it says about the R. The machine stator resistance, RS, is 0.004. And the armature windings are static, they don't move. It's the magnet that's spinning in a generator. So the stator resistance is the same as the armature. So if I needed to solve for P in, it'd be P mechanical loss plus P electric loss plus P out. That's just the power flow diagram. What goes into a system must come out of this system, and it has two parts of loss in the output power. Mechanical loss says 100 kilowatts. 100 kilowatts. The electric loss, and I'm just writing the formula down, but it says 3I squared R. And that makes sense that it's 3I squared R is always real power, but I multiply by 3 because it's all three phases. P out. So if I plug those in, 100 kilowatts plus 3, the I line was 1.92 kiloamps squared. The R was 0.004, and my P out was 900 kilowatts. That all together sums up to make P in of 1044.2 kilowatts, which, if I was putting that in engineering units, would be 1.044 megawatts. So my efficiency, 900 divided by 1044.2, 900 by 1044.2, and I get 86.2%.